the board of directors of the Friends of the VAL who run this place. I'm a former director of the observatory, who retired in January. Life is good after retirement. So, how many people are here for the first time? Wow, excellent. And I'm expecting we have some visitors from out of town.
Why? Because it's flat.
Where it is?
Johns Hopkins University.
Oh, Johns Hopkins. They worked at the Telescope. We're across the street from you guys. And
you know where I'm from.
When I saw them enter, I said, hold on, you guys aren't looking. She's got a Calgary Flames jersey on. We have somebody else from out of town. Oh. What brings you here from Baltimore?
Visiting firm.
Oh, okay. So, my pleasure tonight to introduce our speaker, Breanna Crompvoets. Is that right? Breanna is a doctoral candidate at the University of Victoria. She's studying for her PhD under supervision of the director of the observatory, James Francisco, and somebody else at UVic. But anyway, James is the important guy. Breanna got her undergraduate degree in Regina, and as soon as she finished her undergraduate, she escaped Saskatchewan and came to the West Coast.
Yep.
She's doing work on star formation, hidden stars and what clouds you're going to hear about. She does work with the James Webb Space Telescope. I'm sure people have heard about that. Breanna is also passionate about astronomy outreach and interested enough using poetry as a means of explaining the wonders of the universe to everyone. So I'm not sure if she'll be reciting any poetry tonight, but maybe if you ask her at the end, she will. So we'll let Breanna carry on, and I'm going to turn the light all the way out.
I will not be reciting poetry, but if you really want to hear some, I can take that one. All right, so thank you everyone for coming out to tonight's Star Party. I'd like to just start off with a moment where we're just gonna zoom through the stars for a moment, and I want us to consider why we're here tonight. What brings you a star on August 17th, 2024? Why are we interested in stars? What makes us passionate about astronomy? And I invite you to take like 10 seconds to actually consider, why are you interested in astronomy? Now, you don't have to say anything. Okay. Some of you might have thought, I really want to understand how the universe came to be. Or you might be thinking, is there life out there? How did our Earth come to be? How did I come to be here now on August 17th, 2024 at 5071 West Sandwich Road? And all excellent questions, and except for that particular last one, all aspects of astronomy that people are actively researching and trying to understand. And I'd like to point out that every sort of question we have, if you want to know how life came to be, then you have to know how, planets came to be. And to know how planets came to be, you need to understand how stars formed, because stars came before planets. Again, with galaxies, if galaxies form, you first need to know that stars came first. So star formation is often sort of, it's not, so I'm imagining that there aren't many people out there who thought, I really want to know how stars form, when I asked that question of what draws you to astronomy. Maybe there were, in which case, you should do a PhD, I recommend it. But that sort of brings us to the topic of tonight's Star Party, which is going to be looking into, what star formation is, and we're just particularly going to be looking into it through the lens of the James Webb Space Telescope. So, as Dennis said, I am a PhD student working particularly with the James Webb Space Telescope this is what I am doing my PhD in. So I'm very happy to get the opportunity to talk to you guys about this evening. So, to begin, because I'm a PhD student, I am obligated to put this figure in every single one of my slide decks. That being said, it's got a lot of numbers, it's kind of monochrome, it's not very interesting. So instead, we're going to put on our cosmic chef's hat, and we are going to do an easy bake edition of how to bake a star. With this, we are not sponsored by Hasbro. Hasbro has nothing to do with this. Please don't sue us. So, how do we make a star? Easy bake edition. Well, first off, whenever you're doing any sort of baking, you need to measure out all of your materials. You need to get your flour, your sugar, In this case, we need about 2 cups of gas to 1/8 teaspoon of dust. Now, when I say gas, this is hydrogen, helium, and in our own galaxy, this also includes like carbon monoxide and other kinds of gas. Whereas dust is generally like carbon compounds. And so we get 2 cups of gas, and we get 1/8 teaspoon of dust. And I don't know if you've noticed, but the sun is a bit bigger than 2 cups of gas and 1/8 teaspoon of dust. So we actually need about 10 to the 30 of each of those, which means we need 2 million billion cups of gas and 1/8 million billion teaspoons of dust. In other words, a lot. And so once we get these, we put them into our mixing bowl, and we put it in our cosmic refrigerator at minus 260 degrees Celsius for a couple 100,000 years, which in the realm of space is like a second. But minus 260 degrees Celsius, that's kind of frigid. In fact, that's like only 10 degrees below absolute zero, which is the coldest it can possibly be in the universe. And you let this sit in a cool space until your protostars form. And what this means is that you have to wait until your gas actually goes and undergoes gravitational collapse on its own. So we showed this as a bowl of gas and dust because we're doing an easy bake edition. However, this bowl isn't just sort of, it's not sitting there completely. It's not like your bowl of raisin dough sitting in the fridge. This gas and dust is moving around, and as it's moving around, and since it's very cold, it's getting stuck together. And as it gets stuck together, more pieces get stuck to more pieces until you get dense enough that you actually have enough gravity of your own to undergo gravitational collapse and make those protostars. So why does it need to be so cold? Because we're sort of fighting off the chaos of everything moving in and about. If you want gravity to win, you need it to be cold. You need it to be so cold. And that is colder than Saskatchewan, by the way. And so, yeah, we need it to be so cold in order to overcome gravity. In order to allow gravity to overcome the rest of the forces at work that are sort of pushing the gas in every different direction. Now, once you have these protostars, you can go ahead and toss them onto your baking tray. If you, this is a rather weird tray in that it only holds 8 protostars, but we'll allow it. It's an easy bake oven. It's not exactly proportional. And I'd like to point out that in each of these cases, you see a fairly solid-ish light dot in the center of a larger sphere. And what this is sort of representing is the protostar in the center of a big sort of what we call an envelope of gas and dust, which is then going to continue falling onto the star. This is sort of all of the material that was within the gravitational reach of our protostar. So this is what's getting added onto our star. And you're going to take this tray and you're going to slide it in your easy bake oven, at minus 220 degrees Celsius. This is warm now, by the way. We were at minus 260 before, so we're up 40 degrees Celsius. And you're going to leave it in there for about 10 million years or so. Which again, in the time span of the universe is really not that long. So, we bake it. And, sorry Diana, I have a lovely roommate who likes to bake things without setting a timer. And so what this means is that we check on our baking very frequently. And she's in the audience tonight, so sorry Diana. And so we're going to check on our baking very frequently. We're going to pull a Diana. And so don't worry about the fire on the oven, that's fine. And so we're going to check early. We're going to check after about 500,000 years. And we're going to look inside our oven, and we're going to see that our cookie is exploding. This is actually a good thing. Generally not what you're looking for when you're looking in your Easy Bake Oven, but in this case it is. So what we're looking at is, as your star is baking away and it's taking in all of this gas and dust that's in that big pink or light purple envelope, all of this gas and dust is getting piled on, and it's creating all this energy, and this energy needs to go somewhere. And so because of magnetic fields, it pops out in what we call bipolar outflows, so directly opposite big, like explosive, violent outbursts of energy, which is going out either end of the star. This is a good thing. So we are happy to see this. This means that we have a protostar that is currently being formed. So we leave our Easy Bake Oven going, we wander away, we do our laundry, and we come back in about 1 million years or so. The laundry machine takes a very long time. So you check back in, and now you see that the outflows have started to push this envelope down and up and you're starting to get a disk around our star. This is really good, because now this means that we're getting towards something like planet formation. We're really interested in planets, we're really interested in forming people. That's always nice. And so we've checked back in, we see that we have a disk form, we see that we're losing our envelope, we're getting down to a disk. Awesome. Okay, we did our laundry, let's go wash the car. Come back in another few million years, and now we've gotten rid of our envelope, and we just have the disk. And what we can see within this disk is different features. And these features are actually generally related, or often related, to the formation of planets. So in this figure, we've got two planets in the middle of rings of, or gaps within the structure of the disk. And so these planets have actually cleared out their orbit as they're collecting gas and dust. Now, but this stuff is still falling onto the star. We're still in the middle of forming the star. We're forming planets at the same time, but we're still making our star. And so we're not quite done yet. We leave it in the oven. We know we have to check back soon because we're almost done. So we do so. We check back, and huzzah, we have successfully baked our star. We take it out before it gets burnt, and then it starts on fire, and that's also a good thing. Because stars are, if it doesn't start on fire, then generally didn't get enough gas and dust onto it in order to become what we would consider a regular star. It would instead be called a dwarf star. But we're just going to talk for the moment about what we'll call regular stars. And in that case, we're going to start hydrogen fusion. And that's why our star is now yellow instead of purple, is that we've now begun burning. And so we've got planets, we've got a star. Congratulations, we have successfully built a star. Good work, everyone. You may take off your chef's hats. Okay, that's how we make stars. Where does the James Webb Space Telescope play into it? For those of you who, it seemed like a lot of people knew what the James Webb Space Telescope is, but I'm going to put a little more context for you, bring it a little closer to home. So the James Webb Space Telescope is sort of known as the telescope of the decade. And it has been and it has been a lot of money, it's been a lot of time, it's been a lot of people's effort going into this. 14 billion Canadian dollars or 10 billion US dollars, 14 countries including Canada, 30 years, and over 1,200 people working on it. And that includes people at the National Research Council of Canada, Hertzberg, downstairs, working away at this. And even one of the people there, Dr. Chris Willett, he's actually one of the Canadian project scientists working with the James Webb Space Telescope. So this is a huge multi-country endeavor, and it is something that we're working on in Victoria. We're all working with, I'm working with data from this telescope. We've developed instruments for this telescope that is the telescope of the decade. So good work to Victoria and the DAO for what you've done. It's really fantastic. Now, this is a lot of money. This is a lot of time. This is a lot of effort. But what is it? Well, it's a telescope, and it's cost all this money, effort, and time because we want to send it far away. Well, we have sent it far away. We've sent it 1.5 million kilometers, or about 1 million miles, away from the Earth to what is called L2, which is a point in space that we actually can sort of drag a telescope along with us in our orbit, and it will stay at the same distance from us the whole time. Oops. So this telescope is way out there, and it's operating at, again, minus 220 degrees Celsius, which is the same temperature we needed to, that was the temperature we were baking our protostars at. And this is very cold. And space is actually, space at the Lagrangian point, L2, is not that cold. 1.5 million kilometers is not that cold. It's about 85 degrees Celsius out there. So you have to cool this telescope a ton, which is why it took so long to get out there, because you have all these moving parts. And this silver bit that you see at the bottom of the telescope, this is actually the sun shield, which is what's protecting the instrument from getting, so that it can be minus 220 degrees Celsius. It also has 4 instruments on it that measure different wavelengths, and 39 imaging filters. I'll get into what the imaging filters are in a moment, but the really important part of this telescope, we've had lots of space telescopes out. This telescope, and why it's so important, is because of where it operates, and that is in the infrared. So if you have been so unfortunate as to take a science class ever, you have probably seen this diagram. And all it's showing is sort of the different wavelengths of light and where, how long they are, and what we sort of call each region. And the James Webb Space Telescope operates in the infrared, which kind of means that it's seeing the temperature of things. So if you think about a James Bond movie where the bad guy's watching him run through the trees with his night vision goggles, he's looking at the infrared spectra, and so it's looking at the heat signature. And so that's what James Webb is doing, is it's looking at the heat signature of the universe and of all these different objects. And what this means is that it can see through dust. And so this is an image of, or same image basically, taken by the Hubble Space Telescope, which operates in visible wavelengths, versus the James Webb Space Telescope. And both are incredibly beautiful images. And you'll notice with the Webb that it seems to, I always think that this looks like a great big hand reaching up. And you'll see with the Webb, it seems like he's missing the middle of his hand. And this is because we're actually able to see through the dust with James Webb. So this is super important because we're talking about how stars, especially for my research, we're talking about how stars form in these big clouds of gas and dust out in space, and they form deep within those clouds. So we would like to be able to probe within that. And this is actually an example of one of those clouds, and so we can see through it to where stars are actively forming. So that's really darn cool. Now, that's just a artifact of it being an infrared space telescope. It's not only an infrared space telescope, because there have been infrared space telescopes before. In fact, about 20 years ago, there was the Spitzer Space Telescope. And this, believe it or not, is the exact same image again. One from the Spitzer 19 years ago, and then the other from JWST 2 years ago. Sorry, 21 years ago versus 2 years ago. But 19 years difference between the image. Not much has changed, except for our ability to take a picture. And so what we are seeing is sort of the vast change in technology that's happened in the last 20 years realized in what we're able to do in space. And so I mentioned that there were 39 imaging filters, and this is sort of where they come in. So you see these big red things going way out to the side? That's our outflows that we were talking about earlier. So we're actually able to see those, whereas if you look at the Spitzer image, there isn't a whole lot there. Like there's some bluish stuff, but it's not really clear if there are outflows there. And the reason for this is because of those 39 imaging filters. So we see red, green, blue. That's our color cones in our eyes. But James Webb looks at 39 different sort of selections of color. And so it's looking at a specific selection of color that directly corresponds to what happens in the gas when these outflows hit the gas. As physics, I'm not going to bore you with the physics, but there's a specific, it's only emitted at like a certain wavelength, so you need a certain wavelength to really be able to pick up on these signatures. So Webb is incredible with its availability of these selection of filters. Now, not only is it able to do that, but it has such good resolution. Like what we're seeing here is, again, the same star. There's a bit of brightness in this square. I assure you, there's something, but it compares nothing to the star we're seeing up there. And we can see that to such high resolution that we can see the disk that is forming around the star. That is a star. That's this. That's the same picture. Well, I mean, this is my artistic representation, but it's the same phenomenon that's happening. We can see it happening in real time. We're not going to have our laundry running for a few million years, so we're not going to get to see this one star do its whole thing, but we do get to see it happening, that snapshot in real time, which is fantastic. So, getting towards the end of our time here, the question is, how does Webb actually change our understanding of star formation? A better question, perhaps, is what assumptions do we make about star formation? And the reason this is a better question is because Webb has been out here since 2022, trumping and trashing all of our assumptions about what we knew about the universe. And so we are having to reevaluate our understandings of the universe in many different ways because of this telescope, and it's fantastic. I can tell you there's nothing that a scientist loves more than being told everything they've ever learned is wrong. And then they get to be trying to be the one to find the right solution. So in, I'd say, pretty much all of astronomy, we make sort of three key assumptions. We assume that we have accurate measurements of everything that we need. We assume that we know all the physics, and we assume that what we are seeing, or what we are measuring, is repeatable and representative, which is to say that what we are measuring here is kind of the same thing as what we're measuring here, which is the same thing as what we're measuring here. And these are very different pictures, but because the physics is generally the same, again, we're assuming that we understand all the physics going on, we can actually pull understanding from one thing to another. Now, this all kind of hinges on all of astronomy as we know it was built off of observations, which means that it was built off of what we presumed were accurate measurements of all the necessary details. This is a pretty big assumption, especially if you consider some of those pictures that we just looked at and how different they were from Webb to Spitzer. And so this is the only equation that I will talk about, and I will not talk too deeply about it. But the real question that James Webb is helping us answer with star formation is how efficiently are stars forming? As now we can actually see all of the stars that are forming. We can see the wee tiny guys that are being made. We don't just have to rely on the very big bright ones. And so all of our understanding of how stars form, or the efficiency of how stars form, is based, again, on a number of assumptions. I hope you understand that scientists do things other than assume, but there's a lot of, if you ever take a physics class, you generally assume that a lemon is a sphere for ease of simplicity. But anyhow, we assume that we understand how much gas is available, and that the amount of gas that we're measuring is the same as what was forming when the star that we're looking at was formed. We assume that we know how long ago that star was formed. And we assume that the stars that we're counting now, and we're looking at now, are the number of stars we're seeing. And when you looked at that Spitzer image, there were a lot of stars that we couldn't see that you could see in the James Webb image. And there were a lot of stars that you might not have known were stars that were in the process of forming that you could see in that Webb image. And so this is changing things. This is changing things a lot. This is important. So according to previous data, only about 3 to 6% of entire giant molecular cloud, so all of that mass of gas and dust, actually goes on to make stars. This is probably the most famous image taken by the James Webb Space Telescope, and I don't just say that because it's the first picture of a star forming region, or the fact that I worked with it for 2.5 years. It is, I've seen it on calendars, Facebook backgrounds, Zoom backgrounds, everything. And it's pretty darn famous for a reason. And that reason is because it's showing us star birth as we had never seen it before. And having worked with this image for the last 2.5 years, I can tell you that when we first looked at this image with Spitzer, we thought that there were about 40 stars forming in it. There are over 400 stars forming in this image. That's a big difference. And it's forming from the same amount of gas. But the big thing is that those 400 stars, many of them are wee tiny little guys. So because Webb is so sensitive that it can really see those wee little stars that aren't actually going to go and light up. They're not going to become a yellow star, they're going to become a dwarf star. And that's a whole new region of astronomy and star formation that we'd never really gotten a chance to even consider how it might work. So Webb is opening up new avenues of what science we can do. And along with that, it's changing our understanding of the efficiency of star formation to the point that, according to this new data, about 10% of the cloud goes on to make stars. Now you might say 10%, 6%, is that big? It is a pretty big deal. It's changed all of our simulations and all of our understandings of how stars are made functioned on this idea that 3 to 6% is what you need of the efficiency. And so it changes our understanding of what mechanisms are really at work in the creation of stars. And with that, I'm out of time, so I will leave you with this absolutely gorgeous image of M42 that the James Webb Space Telescope took. Thank you very much.
Thank you to Breanna for the wonderful talk. Very interesting. And by the way, do not rush out and buy an easy bake and try it. Not recommend it. We have time for questions for Breanna. So maybe on her talk or other things. Let's go ahead.
Can you explain what that is?
Yes, this is another image of another star forming region. So we have a very, I don't know if I have a cursor. I do not have a cursor. We have a very big, bright star in the center there, and it is, because it's such a big, bright star, it's blowing off a lot of steam. We'll say it has these big stellar winds that it's pushing off, and that's what's causing all of this gas to sort of pile up. And what we saw with that image, the previous image, was sort of a section of cloud like that, but in a different region.
How far back are you looking at star formation now?
In time? I am looking, well, the James Webb Space Telescope, it depends how you trace star formation. So images like this are all within our own galaxy, so it's not too far back in time. It's only a matter of a couple of thousand years or so.
That's really recent.
Yes. And yeah, so star-forming regions like this are only within the last few thousand years, but you can look at galaxies that are forming with Webb, and that's towards the beginning of the age of the universe.
And
I wonder how the colors groups of the images, who decides which color this one is?
Excellent question. So yes, because the James Webb Space Telescope operates in the infrared, none of these are real colors. All of these colors are assigned. And oftentimes they're sort of shifted, so what is blue versus red is the shortest wavelength versus the longest wavelength, and then you fill it in between. Or they'll choose different colors to sort of highlight the different mechanisms going on. So to go back a few slides, in this particular image, they have red, which is really highlighting the outflows here. And yellow there is highlighting a region of what is called polycyclic aromatic hydrocarbon emission, which is a really long name for, it's a very big molecule that exists out in space. And so that's a whole pocket of it. And it's cool that we're actually seeing that particular signature. So that's generally how the colors are assigned to showcase the different science effects.
So is it done by computer
Yeah.
or by someone?
like all telescopes, Webb takes black and white images. There's a certain filter in front of it, but it ends up with a black and white image. If you look on the light table out there, there's an example of how you make a color image out of black and white images. So they assign different colors to each of the black and white images, and when you put that all together in the computer, voila, you got a color image. So the example out there, there's a black image, there's a cyan, a magenta, and a yellow. Well, it's a Hubble image, and you line those all up, and you see a color image of your line image. So it's producing these beautiful color images. It's almost an art as much as a science. Someone's there to try and get an image that is not only scientifically illustrative, so showing different parts of the physics or whatever is going on, but it's also beautiful. So it's a bit of an art and it's a bit of a science. And there's another question down here.
Yeah, you looked into gas formations into, let's say, brown dwarfs. Have you also seen a combination of brown dwarfs or red dwarfs going into creating something new, and what kind of different out that is?
Like, are you saying when these objects merge?
Yeah, so you get two brown dwarfs come together with one dwarf to make it like what looks like a sun.
Like you're talking about like the at a protostar stage, or like once you have brown dwarfs and red dwarfs?
Both, if you could answer.
Okay. At the protostellar stage, what sort of happens if you have these little nuggets running around is that they'll actually kind of disperse each other because there'll be too much. You need things to be cool and pretty chill, not just cold, but like, yeah, thank you. And if you have these nuggets running around trying to intermerge with each other and they're not big enough, then they're just sort of going to fly apart. Having two brown dwarfs merge can, I think, cause a type 1A?
There's lots of binary stars
Yeah.
that are in our galaxy. the sun's almost unique in that it doesn't have another companion star. Usually they don't merge, they just orbit each other with their gravity. But as the stars evolve, different events can happen. Maybe another star comes by and disturbs the orbit. Sometimes they do merge. Sometimes we have stars that are really close together and have a common envelope with the atmosphere. They share atmosphere. They go around each other. Those will eventually merge, and they just form a more massive star generally. So it's not a common thing, but it does happen.
So these are not the real colors. It's just the.
No, those are not the real colors. So they look pretty.
Yeah.
Just
No,
like
no.
when the star formation is there, there's a disk, right? Why is that like not another color, just black?
Because we can't really see through it. Like when it's this dark, it's so dense that even Webb can't see through it. Yeah.
So one of the things that's interesting is this is optical, and the dust in our galaxy or in nebula molecular clouds, dust absorbs optical light more than infrared. So in the James Webb, in the infrared, we're seeing through a lot of that dust because it's more transparent. So what's really interesting is you see these four stars just above my finger there. Well, there's no four stars over there. That's because they're behind dust, and in the optical, the dust is absorbing the light. We don't see them. But in the infrared, the dust is more transparent, and wow, we see four bright stars. So that's why it's interesting to study all objects in the universe at different wavelengths of light, because you can see different things at different wavelengths. Okay, any other questions? Yes?
Just quickly, so you mentioned the image filters, and you mentioned that there's one that you're specifically looking for one of the these functions of photons.
Yeah.
So that means you're looking for very specific spectrum. Like, what is that? Is that like hydrogen deionization energy? Like.
Yes. So yeah, it's the excitation of the molecule by the outflows are exciting the cloud, and then it's the de-excitation that releases the photons. Yeah.
Wait, sorry, ionization or excitation?
Excitation.
Okay.
Yes?
Critical mass star have to have to create fusion or not?
Great question. I will have to get back to you. I will need to know that question for my candidacy exam.
What's the question?
What the critical mass needed for a star to start hydrogen fusion is.
0.08
Oh, yes.
solar mass. So Jupiter is just slightly less massive enough to be a star. We still think it's contracting at the center, generating some energy, but the lowest, you have to be about 0.08 something solar mass to start burning hydrogen. So just a little less than a tenth of that. Don't ask why I know that number. The numbers stick in my head. That's all. So, Breanna mentioned, that things start out in her easy bake oven as a mixture of gas and dust, and that dust is carbon, oxygen, nitrogen. Well, of course, that's what we're made of. I mean, it goes on to form the sun and the planets, but then we come along and we're formed out of stuff off the planet. So we are made out of stardust, as they say. If you go into the exhibit gallery, there's a little display explaining that in a little more detail. But, so if you have your easy bake oven, you might open it up and see little people in it.
Do you have a question with that?
Pardon me?
Do you have a question with that?
Okay, well, the easy bake oven?
No, about the stars and the planets. How do they differentiate? Like, if they're both coming from the same gas cloud.
Well, the mass distribution in this disk is very highly concentrated. So that's where most of the material goes, into the star.
Yeah.
So then you have this disk of gas and dust, and it's very chaotic, and we think at some point things start happening where pebbles collide and form rocks and things, and all of a sudden you start getting little planets, and then they start feeding out with disk and everything. So it starts out with the sun, the star being there, and just a disk of material, and then things happen in the disk that end up forming planets.
Yes. So with that in mind, with the idea of being able to tell the difference between a star and a planet, and understanding more about the mechanics of how they're made, if you applied AI and other technologies, would that be able to give you more insights into how far the solar system, galaxies, etc., whatever you want to describe it as, you'll have more insights as to how big it is, how far it can go, where it might end, because you've got those building blocks to understand the lifespan and so the kind of mechanics of it.
So planet formation, Breanna's talked on star formation. Planet formation is a whole other subject.
No, I'm just thinking of the same thing with stars. You've gone from this kind of fuzzy picture that you can get certain kind of data from, and now we have this super detailed insight into another view. So from that, you're taking more information about how things are forming. Right. So you're able to kind of apply it across the broader spectrum.
Well, that's one of the advantages of what Breanna's doing, is we can study star formation nearby. When we look at it in distant galaxies, we see it on a totally different scale. So, and we see it at all ranges in between very distant galaxies nearby in our own Milky Way. So the idea is to try and build up a coherent picture of star formation on all those scales. We do know that there's starburst galaxies where star formation is very violent. There's a huge amount of star formation going on. Our galaxy doesn't form that many stars. It forms something like one star a year on average. So it's pretty quiet as star formation goes. Yeah, so I'm not an expert on star formation, and I'm not going any further. Yes.
Your little purple ghost star.
Yeah.
Is that giving out any light? If so, how?
Yes, it is giving out some light. It's very cold right now, so it's like all stars are, well, they can be approximated as what we call black bodies, which is to say that they give off a very spectrum, so this star itself is also giving off that very simple spectrum, but because it's so cold, this is shifted very far into the infrared, which is why we can see them so well in the infrared as well.
My last chance for questions. Okay, let's